Welcome everybody to Bootstrap Surprises. So it's a pleasure to have Tim Hesterberg come and talk here. Tim is both a friend and a colleague. I'd like to tell you a little bit about him. So Dr. Hesterberg is a senior statistician at Google. That means old. Before that, he attempted jobs at an electrical utility, in academia, and also in software. At least he knows how to drive a forklift. He received his PhD in statistics from Stanford, where he played a lot of volleyball. Got his BA in math from St. Olaf, where he proved he can't sing. And claims he studied 2 years in Germany, but has nothing to show for it. He said nix.
Gar nix. Überhaupt nix.
He wrote mathematical statistics with resampling in R with Laura Chihara of Carleton University, and got her to do most of the work. Is that your management style at Google too? He exploited 2 college students and a high school teacher to write book chapters for teaching introstats using resampling. Then added David Moore as a co-author so people would think it was worth reading. David Moore is a well-known textbook and statistician in our profession. He can't seem to stick to one thing, but he's also written about streams and earthquakes, electrical demand forecasting, web traffic, clinical trials, display ads, computer vision, and spiders walking around spaceships. He's a high muckety-muck for the National Institute of Statistical Sciences and the Interface Foundation. He helped write the ASA guidelines for undergraduate statistics programs, and I think part of this talk will resonate with that. And he used as an example in how to give. He was used as an example in how to give a really awful presentation. Which was it? Was it the good side or the bad?
We'll just leave that.
We'll let you decide. He runs or bikes to work, and when he drives, the accident rate in Seattle skyrockets. And finally, just to cap off the accident-prone paragraph, he broke his toe at a math contest. Tim is a tree hugger. He teaches kids to shoot rockets, make kerosene torches, and set rafts on fire. That sounds like mines. Has herded cats. That sounds like Greg's job. Chaperoned high school students to set up computer labs in Guatemala, Ecuador, Costa Rica. His homepage is www.timhesterberg.net. So if you do a search, you'll get there. All right. So
thank you.
Surprise us.
Okay. Thank you everybody for coming. Let's talk about bootstrapping. Let's try again. All right. So why do we resample? Bootstrapping is one variety of bootstrapping. It's easier to understand. And I'll go through, how many of you know about bootstrapping? Pretty well, okay. I will do a little bit of intro for bootstrapping. It's easier to understand, and that makes it easier when we're communicating with people who don't know as much statistics. It's more accurate. Oh, maybe not. What I'll show you, part of what I'll show you today is that the simple bootstrap methods that people think of using when they're worried about accuracy of classical methods, well, those simple ones are not actually very good. But there are variations that are better. And it's easier. It's not like sort of Stat 101 where you've got a different formula for every situation. There's a basic procedure that you use in a wide variety of situations. Okay, and it's computationally expensive, typically, except there are some cases, like at Google, where we do it because it's computationally easier. So I will start by doing examples of doing bootstrapping and see how it works, and then go into some of the Google example and talk about accuracy. So, did some consulting work for Verizon. And how many of you have landlines? Not a few. Okay. So, used to be that everybody had a landline, and you got your phone service from one company. And then it was partially deregulated, so you could get your long-distance service from a variety of companies. But you still got your local service from one company, because we did want a bunch of different companies digging up lines to everybody's homes. And if something went wrong, that one local company was responsible for making repairs. And they were supposed to be fair about it. If you're a customer, a long-distance customer of another company, the Verizon is supposed to make repairs for you as quickly as for you, who's the customer of Verizon. So here we have an example where there were 1,600 repairs made for Verizon customers, 23 repairs made for other companies' customers, one particular competitor, with their average repair times of 8 hours and 16 hours. Looks bad. Looks like Verizon is cheating. Well, the question is that difference statistically significant, or could that be just chance? So let's take a look at the data. Very long tail distributions, a lot of short repairs, and then a few really long ones. So maybe the difference is just because we happen to have a few big, long ones in the competitors. So here we have histograms, a few long observations, and then one big outlier here. And here we have normal probability plots, which I like because we can see all the data. And we see that there's that one outlier. But even aside from that, at corresponding quantiles, the repairs seem to be longer for the competitors' customers. Now there's some odd bends here, wiggles. This is 24-hour periodicity. A lot of repairs made between 0 and 8 hours, not so many between 8 and 24. And then again the next day. Okay, so maybe the difference here is due largely to that one outlier. So, want to look at this, and I'm going to start a little simpler, not with both data sets at once, but look at one data set at a time. We have computed the mean of the numbers. How accurate is that mean? Well, what we'll do is we will bootstrap. We've got a set of 23 numbers. I'm going to take a sample of size 23 out of those 23 numbers with replacement. So it's like putting the 23 numbers in a hat, picking one out, recording it, sticking it back in, picking one randomly. So I end up with some repetitions and some observations missing altogether. And then I compute the mean of those numbers. And I do that again and again, say 10,000 times. And I get the bootstrap distribution. So on the top is the 10,000 bootstrap means from that large data set, 1,600 observations. And they range from, okay, the average is about 8.5, like the original mean. And then we range roughly 7.5 to 9.5. And on the bottom, from the smaller data set, the average is about 16, because that's the sample the population I was drawing from. And there's a much larger spread from 9 to 30. So it looks like the sample mean for that smaller data set is much more variable, much less accurate. Why is that so much more spread out?
Fewer samples to begin with.
Fewer samples, that is by far the biggest reason. Secondly, because the sample is a little more spread out. More variability in that data. And then another thing that we notice is, well, the original data was very skewed, right? But when we're taking a sample mean of 1,600 observations, that looks approximately normal. This is the central limit theorem in action. Conversely, for the smaller data set, there's roughly bell-shaped, but there's clear skewness there. It's not normal. Right? Sample size is 23. If we only had 7 more observations, it would be just fine. So when we see something like this, it's very natural to measure the spread here by standard deviation. And that is the bootstrap standard error. We take that bootstrap distribution, we compute the standard deviation. That is the standard error. That measures how much the mean varies due to random sampling. This is what a standard error is. A standard error, by definition, is standard deviation of the sampling distribution for a statistic as opposed to data. That is a concept that's hard for beginning statistics students to understand. Because in the classical statistics course, they're given standard error and they're given the formula S over square root of n, but they don't know what it really means. And I'm sorry, but it's not just intro stat students. I do a lot of interviews at Google. And you'd be surprised at the number of people who don't understand what a standard error is. And I'm asking them to explain the standard error in a particular context, and they tell me S over square root of n, and it's not even a sample mean context. Okay. So one thing about the resampling, the bootstrapping, is it's nice and visual. We get something concrete as opposed to the abstract idea of a standard error. Here we get to see what a standard error means. So the standard error for the large data set was 0.36. For the smaller data set was about 4. That measures the relative accuracy of those two means. Okay. Also, we can use the bootstrap to estimate bias. Now here we're working with a sample mean, so there's no bias. And the difference between the original observed value and the average of the bootstrap values, this minus this, would be an estimate of the bias. In this case, it's practically 0, not exactly 0 just because of random variation. But for some other statistics, we would observe the bias then. Any questions? Yeah?
Why not just use quantiles of the bootstrap distribution and forget about standard error?
We'll come to that. That is one thing that we do.
Okay.
Okay, other questions? Okay. All right. So yeah.
So in that, you are assuming your observations are IIT, right?
Yeah.
Are they really IIT in this particular setup that you have had? Like,
Okay. In this case, there are a number of repairs, and yes, it's conceivable they're not IID because if all of a sudden there's a slew of repairs coming in, they may not have the repair people to service them all right away. So they could all be delayed because there's just however, that should affect both groups equally. Another thing is that what we're looking at for this particular data set is this whole thing is overseen by the Public Utilities Commissions, and they look at many different sets of data for different competitors, for different time periods, different classes of service. So this is just one of the many results that we're seeing. So it is sort of broken down so that they are somewhat more similar within the group. Okay. Yeah.
So what's the answer?
Oh, we're getting there. It takes me a while. I'm slow. Okay, so what's the idea behind the bootstrap? It's what we call the plug-in principle. If something's unknown, you stick in an estimate for it. This is something we do all the time in statistics. What's the standard deviation of a sample mean? It's sigma over square root of n. In practice, sigma is unknown. We stick in an estimate for it. We stick in the sample standard deviation. So we're using that idea here, with the difference that what we're plugging in is the whole distribution. So here's the ideal situation. There is some population, And we're interested in the sampling distribution of some statistic, of a mean, of a median, of a regression, slope, whatever. We would ideally take many samples from that population, compute our statistic for each of those samples, collect all of those statistics, and that is the sampling distribution. Okay, but in practice, we can't do that. We can't draw many samples from the population because that's too expensive. In practice, what we have is just one sample, and we do the best we can with it. So in the Bootstrap, what we do is we draw random samples from an estimate of the population. Typically, just drawing some random samples from the data. But there are other things you can do. If you believe that there's a parametric family, you could estimate parameters from that, of that family, and then draw from that parametric distribution. Okay, so, but the key idea is create an estimate of the population and then draw random samples from that. And otherwise, repeat everything the same way as in real life. So if in real life you're doing IID sampling, then you want to do Bootstrap IID sampling. If you're doing stratified sampling, you do stratified sampling. Finite population, then you do a finite population Bootstrap. You mimic real life, except for that plug-in principle. Okay. Fundamental Bootstrap principle is this works. That the Bootstrap distribution tells us something about the sampling distribution. But there are limitations. Number one is compare this sampling distribution, this is what we're interested in, to the Bootstrap distribution, and look where the middle is. That sampling distribution is centered at mu. The Bootstrap distribution is centered at x bar. Okay? This is a big deal. This means we can't use the Bootstrap to get a better estimate for mu. No matter how many Bootstrap samples we take, 1,000, 10,000, a million, they're all centered at x bar. They're not centered at mu. We're not using the Bootstrap to get a better estimate. We're not using the Bootstrap to get something out of nothing, create data where it didn't exist before. And some people are suspicious of the Bootstrap because they think that's what it's trying to do. And the name doesn't help. You know where the name Bootstrap comes from?
Pulling yourself up by your bootstraps.
Yes. And you know where that comes from?
Munchausen.
The Adventures of Baron von Munchausen. Yes. Where the Baron had these fantastic adventures, and at one point he was stuck at the bottom of a well, going to drown, situation hopeless, until he came up with the idea of pulling himself up by the bootstraps. Problem solved. So the name implies something out of nothing. Why did Brad give it that name? Anyway.
I think I remember a story where he first wanted to call it the meat axe or the shotgun because it would blow the head off any problem. But then he sort of toned it down.
I developed a variation of the jackknife procedure that I called the butcher knife, and we get violent. Okay. Oh, another variation that was a combination of jackknife and bootstrap that I originally called the jackboot procedure. Jackknife and then a bootstrap from that, but that was too Nazi. Okay, so the bootstrap distribution is centered at the statistic, not at the parameter. Okay, so we can use the bootstrap to get an idea of spread, but not center. And a little more generally, the bootstrap works better with statistics that are pivotal, where we get roughly the same distribution no matter what distribution we're sampling from. So something like theta hat minus theta, there we're correcting for the difference in centers. So just by looking at this, we get an idea of spread. I'll show you a little later, this, dividing by standard error, gives us better results yet. All right, that was the one sample bootstrap. Two sample bootstrap is if you have two IID samples from population 1 and population 2. The way we bootstrap is we draw bootstrap samples from sample 1, bootstrap samples from sample 2, independently. And this is what we get for the difference in means in that Verizon example. Okay? So the difference bootstrap distribution is centered at about 8, like the original difference in means. There's still some pretty noticeable skewness here. We've got over 1,600 observations total. And we're still getting a lot of skewness. Well, kind of what we have here is large population, practically infinite. We've got a really good estimate for the mean of that. It's almost a constant. And then we've got the small sample. So here we've got highly variable small sample mean minus almost a constant. So the behavior here is driven by that small sample. So, is that non-normality a cause for concern? So if you saw this, you were doing some data analysis, you did a normal probability plot, would you worry? Raise your hand if you would worry. Raise your hand if you wouldn't. Okay, so a little story. I wrote this chapter for introductory statistics with co-authors, and one of the problems that we put in there was basically this situation and asked us whether this would be a cause for concern. And the publisher had somebody else do the first draft of the solutions, an academic, and his answer was no. And that's wrong. His background was using normal probability plots to look at data. And if we had this for a set of data, that would be no problem. Okay? Because then when we take the sample mean from that set of data, the central limit theorem is going to straighten things out. But what we're looking at here is the bootstrap distribution after the central limit theorem has had its one chance to straighten things out. So any non-normality that we see here is going to directly result in errors if we're doing normal-based confidence intervals.
But why should we use normal-based confidence intervals? We can use bootstrap.
Okay, so that is one answer, that we shouldn't just do normal-based confidence intervals. Yeah.
Of course, if you get a normal coordinate, you should not use CR curve.
Yeah. All right, so this is after the central limit theorem. Yeah, it is an issue. We can also do statistics other than simple means. Think back to Stat 101, where early in the course you learn about means and medians. And an advantage of the median is it's less sensitive to outliers. And then a little further on in the course, when it comes time to do confidence intervals and hypothesis tests, you forget that you ever learned about the median, because we don't have nice simple formulas for that. Well, with the bootstrap, it's the same basic procedure. You draw your random sample and then you compute your statistic, be it a simple mean or a trend mean or whatever. So this lets us do better statistic, use the statistics that we should use, really, the more robust statistics. So if we do, on the left we have the, oops, this is the difference in means, and you see the spread is roughly 0 to 20. The difference in trend means, standard error 4 versus 2.7, much smaller standard error. The trim mean is much less sensitive to the outliers, so we'd get better estimates if we use trim means in this problem. Okay, though in this particular situation, we don't do that anyway because this is this highly adversarial situation. It's governed by the PUC. If it appears that Verizon is cheating, Verizon will pay large penalties. The competitors would get some of that money. Anything that hints of throwing away data is strictly verboten. So no trimmings here. 2 quick and dirty confidence intervals. The bootstrap percentile interval is you take that bootstrap distribution and you just take the range of the middle 95%. That's your confidence interval. Another quick and dirty interval is you use the bootstrap to get a standard error, and then you do a t-interval using that standard error. So if you're in a situation where you can't compute a standard error, you use the bootstrap. In my main project at Google, we're doing this. We're doing the t-interval rather than the bootstrap percentile interval. It's a fairly complicated situation. In principle, I should be able to compute analytical standard errors, but it would take me a long time, and I would mess it up a few times, and I would check my work with the bootstrap anyway. So we're doing bootstrapping to get standard errors. And the reason that we're using a t-interval rather than a percentile interval is it's a slow computation. So we're only doing 100 bootstrap samples, and that's not enough to do a percentile-based interval. Even with the t-interval, it's not ideal. I calculated that we have basically a loss of power equivalent to throwing away 5% of the data by doing just 100 bootstrap samples. 2% of it. Okay. These are quick and dirty. They're not really that good. Later we'll see better intervals. Okay, now we're going to get closer to the problem, the original problem. Is the difference statistically significant? So now we want to do hypothesis testing. The basic idea in hypothesis testing is you want to draw random samples, but in a way that's consistent with the null hypothesis. And let me show you what we do. We have the 2 sets of data. And our hypothesis is there's no real difference between the 2 populations. Verizon isn't cheating. It's just random which observation ended up in which sample. So we pool the data. It's all one population. And then we randomly split the data. We randomly select 23 observations without replacement out of those, and label those CLEC, label the other ones ILEC, take the difference between the 2 groups, and repeat that 10,000 times. Okay. So, the name is permutation test, so that process of picking 23 is equivalent to randomly reordering the data and then just taking the first 23. And this is what we get. Now we're getting a distribution that's centered at 0. We're sampling in a way that's consistent with the null hypothesis of 0 difference between the 2 populations. Okay. And we get this sampling distribution. And the original difference in means is here. So what this is showing us is this is how often just random sampling alone would give us a difference that big or bigger. That is our p-value. That measures how rare this difference of 8 is. And the logic is, if that's really rare, it would be a miracle for that to occur just by chance, hence there must have been something else going on, some real cheating. Whereas if that probability is pretty large, then it's easily explained by random chance. Yeah.
The permutation test, if you were to go over, without replacement?
Without replacement, yeah. So the randomness comes in and we're taking the data, stringing it all together, reordering, and then random set of 23 ends up in the first set where they won't see them.
So, but before you're using replacement.
When we're doing bootstrap, it's with replacement. Yeah. Okay. So just to compare, the bootstrap difference in means was centered at 8, like the original difference. And this we use for standard errors and for hypothesis tests. And this is from the null distribution, and we use this for testing, the permutation test. And we get a p-value of about 0.17. 1.7%. Now, in this situation, governed by the PUC, the tests are all done at the 1% level. And if substantially more than 1% of the tests come up positive, then Verizon pays a penalty. So in this case, that result is not statistically significant at the specified level of 1%. One nice thing about the permutation test is we can work directly with the difference in means. It's very natural, as opposed to having to work with a t statistic. So, where are we? We've seen a bit of resampling. Nice thing about this is that we get concrete analogs to the somewhat theoretical concepts. So early in Stat 101, we start by looking at data and we do plots. And then later it gets more nebulous. Well, the advantage of this is we get the concrete representations. And so that helps people understand sampling variability, standard error bias, et cetera, et cetera. So nice for education and for communicating with clients. So that next, we're going to do a little interlude looking at a Google example, and then we're going to come back to accuracy. So few of you have seen this from the talk that I gave earlier. How do we make money at Google?
Ads.
Yeah. You do a search for flights to Hawaii, and we show ads. Or maybe not. This is the kind of search I do, latent variables. Look at all those ads. I rarely see ads. Except a few years ago, when I was looking for a new car, I saw way more ads than I was ever used to seeing, and I wanted to see them. So that's what we want to do at Google, is if you want to see ads, then we want to show ads, and if you don't want to see ads, then we don't want to show them. Yeah, we'd make a little more money in the short term, but it also turns you off of looking at the ads altogether. You learn to ignore them. We call it ads blindness. So we want to make this page as good as possible, and we do lots of experiments for this page. When you come and do a search in Google, you'll be in the active arm of maybe 100 experiments, control arm of 50 times that many. We're experimenting with improvements on the search algorithm, improvements on the ads, how many ads to show, font size, color, back-end stuff for serving things quicker, experimenting all the time. And one thing that we would love to have more of in people that we hire would be some experimental design background and expertise. So of the one area in statistics that I would call out as the most attractive for hiring, it would be this. And the way that data is stored at Google is spread across millions, billions of cores. Okay? So the analysis that we do is not like running R on a local machine and having all the data in memory. When we do something, we need to collect results from the different machines and collect those hierarchically and end up with some result. So things like means are pretty simple to compute. We just add the sums up and count things, whereas medians are much harder. Well, in terms of the Google search page, one thing that we're interested in is cost per click, as an example. How much on average are we paid for clicks for a particular search, flights to Hawaii? And computing that is easy. Okay? So how much are we paid for searches on flights to Hawaii by people who live in Minnesota in January? Little story. Back when I was in grad school, was going to school in California, and I went to Minnesota for Christmas, and at the same time, my girlfriend, who's now my wife, flew to Hawaii. And I could have gone there, and it would have been the same price. But I went to Minnesota. I was going to cross-country ski. And I got off the plane, and it was 9 below. And it got colder from that point. And I started looking for flights to Hawaii, but they were all sold out. At the time, though, the Hawaiian Tourist Bureau was very helpful. They were putting pictures of the nice Hawaiian waterfalls in all of the magazines. Okay, that's flights to Hawaii. Okay, computing the average amount that we get paid for clicks, that's easy. But getting a standard error for that is hard. Because the appropriate formula would not be at the click level, it would be at the individual level. And your clicks are not stored all together. You do one search, it's on one machine. You later do another search, it's on another machine. And we want to treat it at the individual level rather than the click level because your searches are correlated. So to use the appropriate formula standard errors, we would have to restructure the data so that every individual's observations work together. And that's expensive. So what we do is bootstrap it. So think back to the bootstrap, where we've got n observations and we take a random sample of size n. So I imagine that's the people in this room. And I'm going to randomly select a sample of people. So I randomly select someone, I select someone else, and then I get a repeat, et cetera, et cetera. So one way to store the data is which observation got picked each time. But another way is to just count how many times each individual is stored is in the sample. Okay? So the frequencies. And each frequency is binomial with parameters n and probability 1 over n. And we can approximate that with a Poisson. We've got large n here. And so we can generate a bootstrap sample by looking at one person at a time and assigning a frequency to that person. So that's essentially the way that we're going to bootstrap here. A frequency-based bootstrap. And so given the frequencies, say that you had 3 searches to Hawaii, and in a particular bootstrap sample, the frequency for you is 7. We get 7 copies of those 3 searches. Okay, now that in itself isn't all that we need to do. The other thing that we do is we do things on the fly. So when we are running across the different servers and we come to you, we take your cookie, hash it, use that as a random number, use it to generate the Poisson frequencies for the 1,000 or however many bootstrap samples, and add that many copies of your data to each of the 1,000 accumulators. And then we go and we do other servers, and then we come back to another server where your data is represented, where there's one of your searches. And what we do is we regenerate the random numbers and regenerate the frequencies and add those in. So we don't actually have to store those frequencies. We just generate them on the fly. And so by doing that, we end up getting the answers that we need much more efficiently than the formulas. Any questions?
So how do you you said one user's data may be on different servers.
Yeah.
How do you, I guess that's a hard software engineering problem that Google has solved.
Oh, it's just when you do a search, whichever server is available processes your search.
Okay.
Yeah, and yeah, there's a lot of software engineering. There's load balancing. And
But in order to assemble information on a certain user, you have to go through
if we
several.
wanted to collect information on an individual user, we would have to run across all the servers
Yeah.
to find searches by that user. Okay. So this was an example where even though you may think of the resampling as expensive because you have to compute your statistic not just one time, but 1,000 or 10,000, here it ends up being faster than using a formula because of data storage. Okay. Any questions on that before we move on? Yeah.
So I know like YouTube will give you personalized recommendations. If your data is spread out all over the place, how do they like construct a model of what videos you like to watch?
I don't know how the data is stored for YouTube.
Okay.
So I don't know whether that's done on the fly or whether they're doing some batch processing to keep records that when you sign in, that they can associate it with you. Yeah.
Do you mean the standard error being computed online?
Yeah. Yeah, question was, so is the standard error being computed online? And by online, I presume you mean running across all the machines. Yeah. And so the answer is yeah. Other questions? Okay. So now we're going to look at accuracy and starting with proof by picture to give you an idea where the bootstrap is accurate or not. And then we're going to do a little more theoretical. So there are two sources of variation in a bootstrap sample. One is that the original sample was random from the population, and the other is that you're doing random bootstrapping. And how big are those two factors? So here's the situation when we have fairly large samples. What I have at the top is a population, top left. On this side, there are 4 samples from that population. This is the true sampling distribution, in this case, sampling distribution for the mean. Here we have a bootstrap distribution from that sample, and similarly for the other samples. And so let's look at that much first. So, question is, how accurate are these bootstrap samples for estimating that sampling distribution? And what we see in this case is the means, the centers vary according to the corresponding sample, but the spread is pretty much all the same, and the shape is pretty much all the same. Okay. So that is related to that first question. What is the variation due to variation in the original sample? The second question is, you do random bootstrapping. So here we have one sample from that population, one bootstrap distribution. And that was with 10,000 observations, 10,000 bootstrap samples. Here we have 3 of them with 1,000 bootstrap samples and 2 more with 10,000. So they're all giving pretty much the same picture. The ones with 10,000 samples are more accurate, less random variability there. So they're all estimating basically the same thing, but more samples is better. And depending what you're doing, if you're just concerned with standard errors, 1,000 is great. If you're concerned about tail probabilities, then 10,000 or more is better. Okay, so the bootstrap distributions are centered at the x bars, not at mu. The shape and spread of the bootstrap distributions are pretty consistent. And if you're doing 10,000 samples, that's pretty good. Any questions? Yeah.
I was wondering, just looking at all these graphics and all these statistics you're showing, what is your preferred statistical analysis language? Is it R, Python?
I do most of my work in R, and in terms of Google, we've got a lot of people using R. Got about 2,000 people on our R users list. However, there are more people using other languages, including Python. In my particular group, we're going to be switching from R to Python because the software engineers are more used to using Python. Python is a better language in terms of reproducibility and speed and software engineering and tools for testing. And so if we prototype things in Python rather than R, we'll be able to move more quickly from prototype to production. And the statisticians will work more effectively with the software engineers who know Python.
Yeah. So I've heard that MIT just released a new version of Julia. So that's Google has a new
Google uses many different languages and tries new experimental languages all the time. I haven't seen a lot about Julia at Google. Okay. This is smaller samples. Again, working with the sample mean. So now, if you look at these bootstrap distributions, the spreads vary quite a bit more because the spreads in these samples vary quite a bit more. And the shapes also vary more in the bootstrap samples. Okay. And then finally, 10,000 samples is great, 1,000, depending on what you're doing, is pretty good. Hey, then, so small samples, the shape and spread of the bootstrap distributions may vary substantially. Now, that isn't any different for the bootstrap than it is for classical methods. When you do x bar plus or minus 2 times s over square root of n, the s varies a lot when the samples are small. And that's why we use a t quantile instead of a z to give us a little more fudge factor for that extra variation. All right, sample median for an odd sample, odd size sample. This is the true sampling distribution for the median from sample from that population. And these are the bootstrap distributions. Whoa. So now we've got a sample size 15 and we draw a bootstrap sample from that. So we get some observations repeated and some omitted. And then we take the median. Well, the median is the 8th largest of the bootstrap sample. It has to be one of the original values. So that's why we're getting such discreteness here. And so any odd things in the original samples, like a big gap in the middle there, come across in the bootstrap distribution. So the bootstrap really isn't that good for median of a small sample. And it depends too heavily on a few values. And that's kind of a more general problem situation with the bootstrap. The bootstrap doesn't work so well when the statistic that you're computing really depends on just a small subset of your data as opposed to the data as a whole. So it doesn't work so well for median and small samples, even worse for extreme quantiles. And then let's talk about what happens with skewed populations. So here, we're back to working with the mean. And the population is skewed. And here we've got 5 samples. And in this case, I've ordered the samples by the mean of the sample. And so what we see are the bootstrap distributions are centered at the original mean, so further left coming down to further right, and the spreads also depend on the spread of the original sample. Okay, so what does this mean? One thing is that the bootstrap estimate of standard error here, well, you're going to get a pretty different answer. If your x bar is big, you're going to get a big S. Okay, now that's actually not any different between the bootstrap and classical formula methods. Another thing is that if you do a confidence interval in this situation, you will tend to undercover here. When you get a small x bar, then you get a small s, and whether you're doing a t-interval or whether you're doing a bootstrap interval, the interval's going to be narrow and you're going to tend to miss the value. So if you're doing a 95% interval and you want to miss 2.5% on that side, you're actually going to miss a lot more than that. And on the other side, you won't miss enough. With me there? Okay. That is the sampling distribution for the mean. Let me come back in just a bit. So there's a mean variance relationship. The spread depends on the statistic. That has a big effect on confidence intervals. Those quick and dirty intervals or a classical t-interval, they're all not very good. Something that's much better is a bootstrap t. So here the idea is that instead of bootstrapping just x bar or x bar minus mu, we want to bootstrap x bar minus mu divided by a standard error. So the t statistic is theta hat minus theta over s. And then we estimate that by bootstrapping the bootstrap theta hat minus the theta hat from the original sample. Okay, x bar from bootstrap sample minus x bar from original sample, divided by a standard error computed from the sample. So we're using the bootstrap to estimate the distribution of this t ratio. And when we do that, we get these bootstrap distributions, and note, they're great. They're very close to that original distribution. So that is the true distribution for a t statistic. No, t statistic doesn't mean t distribution. Okay. So the bootstrap is very good here. Okay, and then we'll see that practice in a bit. Okay. Now, small samples, I showed you that the bootstrap spreads varied a lot. And when you do a classical t-interval, we use a t percentile to give us a fudge factor to sort of compensate for that variation. If you do a bootstrap percentile interval, you're missing that. People tend to think of doing a bootstrap percentile interval for small data where they don't want to trust the central limit here. But that's actually counterproductive. Because when you've got a small sample, the bootstrap percentile interval is way too narrow. The bootstrap percentile interval is roughly like doing x bar plus or minus z instead of t. You're missing that fudge factor. And then computing a standard error, it's like if you were to calculate s with the divisor of n instead of n minus 1. It's a little narrow, a little too narrow. So the bootstrap percentile interval ends up being too narrow. There's a remedy for that, which is that you can just use an adjusted percentile. So you want to do a 95% interval, instead of using the 97.5% quantile, maybe you need to use the 98. Any questions? This is how bad that is. So we're doing 95% intervals. We want to miss 2.5% on each side. And if you do the bootstrap percentile interval with a sample size of 10, even in the ideal situation that the population is normal, you end up missing twice as often as you should. You're way undercovering. You're doing a 90% interval when you want to do a 95%. Okay. Whereas if you do the little correction, modifying the percentile levels, you end up getting much closer to the desired coverage. Whereas the T interval, or what's called the bootstrap T, they're really good. Okay, so that I've been talking in terms of confidence intervals, but the same thing happens in terms of tests. So think back to the Verizon situation. If we do the permutation test, we get a p-value of about 1.8% using 500,000 replications. And if you do a t-test, covariance t-test, it gives you a p-value of 0.5%. They differ by a factor of 4. Okay, now when they differ that radically, which one do you trust? T-test.
Yeah, I trust the t-test.
Trust the t-test. Well, historical note. When Sir Ronald Fisher was initially promoting the use of t-tests, he said that the t-tests are only valid to the extent that they approximate the answer that the permutation test gives you. The permutation test is exact. The t-test is only exact if you have a normal population, and it doesn't handle skewness well. Why use the t-test? Well, because the computers of that day were just inadequate to doing permutation tests. The computers of that day were young women. We don't have that same limitation now. So the permutation test is the right answer. And if you have unbalanced samples and skewed populations, the t-test can be very far off. If you have balanced samples, equal size samples, then the skewness cancels out, and the t-test is great. Okay, n greater than or equal to 30, population is skewed. Is it okay to use a t-test? Well, the rule of thumb is if it's not too skewed, then yeah. Well, how big is not too skewed? So in practice, what we do is we just go ahead and do t-tests, right? Well, this goes back to what I told you about the first draft of the solutions. People just aren't used to actually looking at diagnostics that would tell us how far off the t-test is. And so the bootstrap gives us those diagnostics. Okay, how big? A problem is this. If the sampling distribution, if the population is normal, X bar and S are independent. Sound familiar? If the population is not normal, if it's skewed, that isn't true anymore. When you have a skewed population, when you get a lot of observations from that long right tail, then both X bar and S are big. So X bar and S are correlated, and this correlation does not go away as the sample size gets bigger. So the better bootstrap procedure is the bootstrap T. And what we do is we estimate the distribution of the T statistic by doing bootstrapping. And here, for example, is the bootstrap distribution if we just look at the 1,600 observations, just the one sample. So way bigger than 30. And if you look at the normal probability, or the t probability plot, just eyeballing it, it looks roughly straight. But if you measure the probability, what fraction of observations fall below the t quantile, the 2.5% t quantile, it's actually 3.9%. It's pretty far off. And this is with 1,600 observations. It's way bigger than 30. Okay, so the bootstrap t procedure says, yeah, we'll use a t statistic, but we're not going to just assume that it follows a t distribution. So instead of using the table in the back of the book, we'll do bootstrapping to find out what the critical values are. And then we'll use those critical values. We'll go x bar minus one critical value times s, and x bar minus a negative critical value for the other side. And so that ends up being, in this case, x bar minus 1.79 or x bar plus 2.11 times s over square root of n. And that will give us a better interval. So now, 1,600 observations wasn't enough for accuracy in that problem. How big a problem is that more generally? That was a pretty skewed distribution. So, how big does n have to be? Rule of thumb is 30. Okay, so I'll pose this problem to you. Imagine that the population is exponential. So kind of skewed, but at least it's an exponential tail. It's not a real long, heavy tail. A lot of the data that we deal with is longer tails than exponential. Okay, so exponent skewed, and you want to do a confidence interval, 95% confidence interval. You want it to be reasonably accurate. Ideally, we would be to miss 2.5% on each side, and so you want to be within 10% of that, 2.25 to 2.75, that range. How big would n have to be in order for a t interval to be that accurate? Sample size 30, is that enough? Raise your hand. How about 50? 100. Who thinks 100 is enough? 200. 400. 1,000. I think 1,000 would do it. Okay. 5,000 observations.
Wow.
With skewed data, the central limit theorem operates on glacial time scales. It's very slow to converge. And there are procedures, the bootstrap T, or there's a Jazz article by Johnson, a skewness adjusted T statistic, much better. But classical T is just not very accurate for skewed data. So what we have here are sample size, the one-sided non-coverage. This is the 2.25 to 2.75%, and this is how quickly different procedures converge. The t interval is the solid line, and this is the same plot except with a different scaling. So we see it takes around 5,000 before that is accurate enough. The bootstrap percentile interval, that's a little better, but not a whole lot better. That's this dotted line, dashed line. Okay, maybe 2,500 observations before that's good enough. So it's a little better, but it's really not what you want. Whereas the bootstrap T is converging much faster. Is this surprising? Yeah, a lot of the statistics that we do in practice is just not very good, and people don't realize how bad it is. It's sort of the situation where we've learned from our professors, who've learned from their professors, who've learned from their professors, and nobody has really taken a careful look at this. And in part because we didn't have the computers available to do the careful look. Except there were theoretical approaches that showed this fact. Okay, why isn't this known? Having the bootstrap available for diagnostics helps a bit. The calculations, so I started grad school in 1981, bootstrap was hot then, Efron was my advisor. If I had done some of the calculations I've done recently using the Department of Vax back then, it would have taken around 20,000 hours. So we just weren't doing that. Okay, and there's some sour grapes here too. We maybe knew it wasn't right, but we didn't know what else to do, so that's what we did. Johnson 1978 Chasm has an article with students adjusted t-statistic. All right, so just for comparison, these are the two plots I showed you before. This is when the population is normal, how quickly things converge, that bootstrap percentile is not so good. This is when an exponential population, and it's much harder. And the only thing that's really working well is this bootstrap here. All right, so wrapping up. Why do we want to resample? It's easier. You don't need different formulas. In my problem at Google, it's logistic regression where we're comparing two different groups. It's complicated. We bootstrap. Can be more accurate, provided you use the appropriate methods. So not just the percentile method. Use the bootstrap tree. And we get these nice pictures that make it easy to communicate results with students or with clients. Good. And if you want more information, you can go to my homepage and there are various references, and you might be interested in our book, the one that Laura jarred in most of the work for. All right, that's it. Any questions?